So, as I say, I'm Massimiliano Materazzi, so I will give you a little bit of an overview of what we do at UCL with relation to waste, how these is seen as a resources and how that can be used to produce fuels or other products in line with basically all these sustainability direction that the world is taking. Okay, so let's start now with the easy way, just basically showing what the problem is that I'm sure all of you are aware of. So let's get it straight. We do produce a lot of waste globally. So currently, the latest figures from last year were approximately 2.5 billion of tons of waste generated globally, and the projections don't show any improvement in that. By 2050, the World Bank institution estimates that the world will basically generate 3.4 billion tons of waste. That's a huge amount. Or imagine like a big mountain of waste, which is basically unsafely disposed, and in most cases, in 40% of the cases, is either landfilled or openly burned. Okay, that's definitely a big problem from the environment from many perspectives. Okay, there is obviously leaching of contaminants through contamination of the soil, of the ground, and the water. Okay, by the action of heavy metals and other contaminants that are in our everyday waste that we generate. Not only that, the landfills globally happens to be also the third largest source of anthropogenic methane. Okay, and methane, as I'm sure you are aware, is a very strong greenhouse gases. Okay, 86 times more powerful as a greenhouse potential, warming potential than CO2. Okay, in a 20 years time frame. So absolutely, this is a big and huge environmental problem, and this without counting all the other surrounding challenges which are associated with unsafe disposal of waste, which waste is a flammable material, and we will see these in more details shortly. And so that can easily catch fire, and so release these contaminants in the atmosphere, and it does represent a big health and safety hazards and risks. Waste does contain plastics, and these plastics is dispersed into the environment and can cause many problems in the wildlife, especially in our oceans. And plastics can degrade into macroplastics that can contaminate the entire food chain. So this is absolutely a big problem of today. Now, the first challenge is how can waste management be more sustainable? Okay, there is this hierarchy, this pyramid that shows you 5 different levels at which waste can be dealt with. Okay, the first and foremost important one is reduction. Okay, we want to reduce the amount of waste that is produced from the onset, perhaps using less materials in designs and manufacturing, and keeping products for longer, or even use less hazardous materials. Okay, so first things is try not producing waste. Okay, so trying to reduce the amount of waste that we need to deal with. The second level is reuse. Okay, make the reuse factor an important one, just by perhaps by some sort of cleaning or polishing or repairing. If it doesn't work, fix it. Don't bin it, and refurbish. So basically, that you can give a new a prolonged life to your item or your good. Then we have the recycling. So that's basically converting this waste into a new products or a new items. Level 4, recovery, which is basically when you transform your waste into heat or energy or fuels, okay? And the 5th level is landfill, okay? Landfill, so just basically dig a hole in the ground and get rid of your waste. Now, unfortunately, for a large part of the last century, in the 1990s and still today, that's the way in which all these 5 categories are levelized is basically like this pyramid is showing. So the largest amount of our waste, unfortunately, is landfill. And then just moving upwards, when it's not landfilled, is incinerated. When it's not incinerated, as a minor fraction is recycled. And still the reuse and reduction approach are not that strong yet. So what we need to do is basically flipping this pyramid upside down and obviously reverse this order. So absolutely, first and foremost, reduce the amount of waste that we produce, try to enhance reusing and recycling practices. If these are not possible, then you will have the recovery and try to avoid for as much as possible the landfill option. Okay. Now, thermochemical treatments, these will play a major role in the future because that kind of sits in between recovery and recycling. Is also known as a chemical recycling because you can, using thermochemical processes, and I will tell you a little bit about this, you can convert this waste that cannot be recycled, okay? You can convert into fuels or even new materials, and that's why it sits in kind of in between. And that will be absolutely critical in the future to get to this nice pyramid for a more sustainable waste management approach. The second big challenge, which might not be directly seen as related to waste, but trust me, it is our road to net zero target, okay? As you might know, that the UK are very heavily committed in trying to get to the net zero carbon emission by 2050, okay? And many other countries in the world are aligning with this to this target, okay? That's not, is a very ambitious target, but it is possible, okay? Just think about it, that the current emissions, global emissions in the UK, annual emissions are almost 50% less than they were in 1990s, although the country has obviously developed and progressed. So this is possible, but go to zero, net zero, that's a very ambitious target. Only last year, 351 million tons of CO2 were emitted in the UK only. Globally, you have to increase this figure by 100-fold, okay? And this is more or less how these CO2 emissions are distributed. You can see that there is a large part of these emissions being associated to the power sector, industries, domestic heatings and buildings, road transport, agricultural, waste management, and aviation. Okay, so that's pretty much how, at least in the UK, these emissions are distributed. Now, for 2050, we need to lower all these blue bars very close to the zero level, okay? That's what basically the net zero target is saying. Well, currently, the brightest projections tells us that basically you will be able to get close to zero in many of these sectors, thanks to the establishment of the new renewable energies like wind, solar, geothermic, hydroelectric, and so forth. Okay, so you can see that the power production, CO2 emission associated to power production will get very close to zero, and equally by the industrial processes, domestic heating, and road transport, also thanks to the advances of electrification and batteries, as you might have seen in some other very interesting lectures in the previous days. Okay, but just look at the right side of the graphs, there will be 3 sectors for which total decarbonization will be very, very difficult, okay? These are the agricultural industries, the waste management, and aviation, okay? The reason is pretty simple. I mean, starting from agriculture, that's obviously takes into account the land use and will still relies quite significantly, obviously, on agriculture for food production. Okay, that's unavoidable. We still produce a lot of waste, no matter how we push further the recycling practices. We still produce a lot of waste, and obviously, as I said before, that's associated to a significant amount of CO2 emitted into the atmosphere. And then we have aviation. Aviation is a very big problem of these new, let's say, new centuries, okay? Because aviation is one of those transport sectors for which an electric alternatives is still very far away, okay? Especially for long-haul flights, a big batteries is still very far from being reality, and the reality actually says that there are no green alternatives to jet fuels at the moment, or very little, okay? And that's where we basically need to act significantly to try to get the net zero target. Now, to get to the net zero, you need to offset these emissions, and that will only be possible by using by having negative emissions. What does it mean? Trying to sequester CO2 from the atmosphere and store it forever underground. Okay, so that's what is brutally summarized with the carbon and capture and storage techniques, CCS. But we also, with the current CCS technologies and techniques available, it will be very difficult to offset all that amount of CO2 produced. That's why we need an immediate and short-term solutions to basically try to reduce those emissions. Now you can already understand how, you know, waste and aviation, you get all those emissions, and we can potentially, why not catching two pigeons with a stone and trying to solve the same problem at the same time. See if you can convert that waste into jet fuel. Okay, so yeah, you can start seeing what's the rationale behind all these waste to fuel concept is. Now, you might be wondering, well, okay, so where does chemical engineering fits into this? Okay, what does have chemical engineering to do with waste management or the net zero target or reduction of CO2 emissions? Well, you have to trust me on this. This is 100% chemical engineering, okay? And chemical engineers will have a fundamental and major role in getting solution to the two challenges that I've presented to you, okay? So more specifically, we are, as a chemical engineering community, and more in particular here at UCL, we're trying to deliver the fundamental understandings to advance these waste treatment technologies, so to provide global industry with the underpinning science from which to develop a more sustainable recycling or recovery practices for the future, okay? So to try to solve the two problems. How do we do that? We try to align with the waste hierarchy pyramid, okay, the second one. So trying to reduce the amount of waste from the onset, but we'll obviously end up with a fraction that cannot be recycled, okay? Not everything is recyclable, or not everything is easy to be recycled. So you take that fraction from recycling facilities, okay? And you deliver that into a plant, a thermochemical plant, which use one of those technologies: gasification, pyrolysis, hydrothermal liquefaction, catalytic depolymerization. There are several of these, okay? To convert, to basically recycle the carbon harvested in that waste and converting into something useful again. These can be green chemicals, it can be low carbon fuels or biofuels, or even new polymers, okay? So that will be the further steps into the waste hierarchy, falling well within the chemical recycling part, okay? So you can see how thermal processes can play a major role into solving these So just a little bit of what we do at UCL. I lead the thermochemical fuel lab at UCL, where we basically assist industries in developing their thermochemical processes at many levels, from testing catalysts to proving these working at pilot scale, reactor engineering, so reactor design, process optimization, and modeling studies. Modeling both on the computer fluid dynamics, kinetics models, process simulations, but also models to make projections of what the sustainability of the plant is, what's the impact in the full life cycle of the processes. Okay, so we kind of cover all these steps that will enable the transition towards a greener future in the coming years. Okay, just now to give you a little bit of an overview and some case studies we have worked on. So yeah, that gives a little bit of flavor of what practically we do to tackle the waste problem and the carbon emissions problem. So as I say, everything starts with a feedstock. So obviously when I say waste, don't think about your black bin bags of garbage that you produce every day, okay? Because that still contains, I hope everybody of you does some extensive recycling, but there are some recyclable fraction also in your unsorted waste, okay? So that is delivered to mechanical recycling facilities, where basically all the recyclables are separated and sent to our recycling facilities, okay? So we don't, thermochemical process don't deal with you know, PET, plastic bottles, or everything that can be recycled, okay? Because if you remember the waste hierarchy, that's more important, okay, than recovery. But we do indeed deal with that fraction that is not currently recyclable, and from that we crush it, we dry it to reduce the moisture. We try to remove as much of inert materials like stones or piece of glasses, okay? So they don't have an energy content, so they can be removed if possible. What you are left with is that feedstock, a perfect feedstock for thermochemical treatment. That is normally called refuse-derived fuel, RDF, okay? In some other countries, it's known as a solid recovered fuel. So it has different acronyms, but that's basically what it is. Is the waste fraction after you removed all the recyclable materials, you've crushed it, you've dried, and that's ready to be used. Why this is important? Well, one is the immediate advantage of this, you know that, because that comes from waste. So you divert waste from landfills, avoiding all those problems associated to methane emissions, plastic degradation, and so forth. And you give a new life to that waste fraction, okay? Only the UK sent 15 million tons of waste to landfills every year, or even 3 million tons per year of RDF, which we don't use in-house, but we exported elsewhere in Europe for waste-to-energy facilities, okay? So that feedstock, it's a locally available feedstock. It's cheap because it comes from waste feedstock, low-value waste feedstock. And so it basically ticks all the three elements of the sustainability product, which has to be environmentally friendly, it has to be affordable, so low cost, and it has to be locally available. Okay, it has to be an abundant source that are able to meet the demand. And so RDF is a perfect feedstock for that. Also, as you can see here, almost 50% in weight of RDF is made of carbon and hydrogen, which are the building blocks of everyday materials, of polymers or fuels or or plastics and everything. So that's absolutely a resource which we need to harvest and make best use of. It has a very high calorific value, very high energy content. So it's really a big waste. Forgive me the use of redundant words, to not to use these feedstock. Okay. Now the flagship of thermochemical processes, and the one I personally work mostly every day with, is gasification. Gasification is, as the terms suggest, is the conversion of a solid feedstock, like RDF in this case, into a gas. Now, incineration does produce gas too, okay? But that's produced mostly CO2 and steam, amongst other contaminants, okay? So that they don't have value. The only value you can get from incineration is basically produce a high level of heat that you can recover with the steam cycles to produce electricity, okay? But the efficiency of incineration is not, I would say, is better than landfill, but is not good enough to justify the use of the RDF, okay? So gasification is potentially has a much wider spectrum of application, because it does produce a gas, but that gas, which is also called the syngas or synthetic gas, is a mixture of carbon monoxide and hydrogen, okay? Carbon monoxide and hydrogen are the building blocks of all the current biorefinery concept. Hydrogen itself is an important commodity, okay? And is an energy vector that will find a huge use in the future to decarbonizing heating and transport too. But hydrogen can be combined with carbon monoxide to produce hydrocarbons. And these hydrocarbons can be hydrocarbons for fuels, hydrocarbons for new materials, hydrocarbons for chemicals, or hydrocarbons to produce electricity in a more efficient way, okay? So gasification, that's absolutely will be one of the key technologies that in the future you will hear about these often and more often in the coming years, because that's the way how you can make the best use of waste. Obviously, there are some challenges, some like political and commercial challenges, but also some technical challenges, okay? Waste is not an homogeneous feedstock like, for example, coal or petroleum fuels or even biomass, okay? Waste is a very heterogeneous feedstock. You know, it changes and fluctuates in compositions due to seasonal variations, but also, you know, depending on where the waste coming from, might have a little higher fraction of plastics or a little bit higher fraction of food waste. So that obviously make the compositions not consistent. So that's represents a problem for thermochemical processes. It does contain a lot of ash, and that's another problem, and I'll show you shortly why that's a problem. It does produce a number of heavy hydrocarbons, which like fools that clogged your unit operation. These are collectively known as TARs. Okay, that's also problems you want to avoid, and obviously the gas will need to be very clean, all right? So you need to get rid of sulfur and chlorine and other contaminants in order for that to be used for fuel or advanced catalytic processes, okay? There are other elements associated to energy efficiency or the scale of the plants, okay? But it would take me too long to explain why that's a challenge too for waste. So let's just focus on the first few problems. Now, gasification itself is not a new process. It has been used for decades. Okay, the first gasifier was patented in Germany in around 1926, and at the same time, more or less, the first Fischer-Tropsch process was patented. That's basically the process that proves that carbon monoxide and hydrogen can be combined to produce hydrocarbons, okay? And that have been these two technologies, gasification, so converting solid feedstock into carbon monoxide and hydrogen, and Fischer-Tropsch, converting carbon monoxide and hydrogen back to usable hydrocarbons, has been used, as I said, for decades to transform, for example, fossil fuels like coal into liquids, or gas, natural gas, into liquids. You know, in Germany, the Second World War, 30% of the fuel that were used were actually produced from coal, okay? Because they didn't have Germany is not an oil-rich country, but is a carbon-rich country, a coal-rich country. So they have used these technologies. Now, how to extend the use of these technologies to produce fuels from waste? Okay, that's a different subject, another matter. And there have been some progress in the last few years. There have been a couple of demonstration plants in Canada and Edmonton that use transform waste into methanol, for example. Or there are some very recent new applications in the US, in Nevada, or even here in the UK that are trying to use waste gasification coupled with Fischer-Tropsch to produce, for example, jet fuel from waste, okay? And that basically will help solving the two challenges I mentioned at the beginning. So that's an important, you can see how this is getting, momentum is getting very, very important applications in the futures. Now, the first step is the so-called gasifier, okay? This on the left side is a fluidized bed reactors. We have an entire dedicated module at Chemical UCL, which I teach in the 4th year, an MSc program, which is fluid particle systems, to design effective fluidized bed reactors that convert these waste materials into gases, okay? Gasification comes to sit between in combustion and pyrolysis. You have some oxygen, not as much of oxygen you need to fully burn the fuel, but enough to get to the right temperature between 750 degrees and 800 degrees C to convert this waste into syngases, okay, hydrogen and carbon monoxide. But you have to do that being careful how to deal with the solid materials, how to deal with the ashes that are associated to waste and hydrocarbons that are emitted, okay? And that's what our fundamental work at UCL is based. We have a different scale gasifier, gasifiers, and we use advanced imaging techniques to see what happens inside the reactor and study the evolutions of these waste when it enters into the reactors. You can see from these two videos how RDF and, for example, coal in the same reactor in the same conditions behave very differently, okay? Waste is a very highly volatile material, mostly due to the little plastic content that it has, which produce these flames, which makes the control of the reaction a little bit tricky. And that's where we are working basically with advanced imaging techniques using X-ray and try to track the evolution of the particle inside the reactor to basically design a new type of reactors which are more efficient and can deal with heterogeneous feedstock like waste. You also have to deal with the solid matters, with ashes and metals that are formed, which can cause operational problems in your reactor. So we also operate on other complementary technologies, including plasma, high temperature plasma. Plasma is the fourth state of matters, it's above gas, is where basically temperatures very high that are able to destroy all the organic contaminants within your gas phase and melt the ashes into a liquid and stable form. So the ashes are collectively collected as these ceramic materials, which basically it's totally inert and can be either disposed or used construction materials or for new materials. So in line with the circular economy approach. Okay, so you can see how different technologies, coupling these technologies together, you can basically convert these waste into a usable and clean syngas that then can be utilized to produce a plethora of new sustainable low carbon products. Okay, when I say low carbon products, is obviously they can be bioproducts, they can be biofuels, but we need to take into account that waste does also contain a fraction which is not bio. Okay, that's specifically related to the no recyclable plastic fraction. Okay, so that's, I say, low carbon. So it's not 100% biofuels, but it's still much better than other alternatives, which, as I show you later. And at UCL, we scale different techniques at we test different techniques at different scales, from small industrial units to small scale reactors, to study what's the underpinning science and mechanisms behind this. So to basically to make this an effective reality and to help industries to deliver large plants. Okay. I conclude this presentation with a little bit, with a small case studies we've been working more recently, how to convert waste into bio-SNG. SNG stands for synthetic natural gas, so methane and biohydrogen, okay? So we have worked in the past with several industrial partners to prove at demonstration scale that refuse-derived fuel coming from materials recycling facilities can be gasified, can be cleaned, and then transformed into biofuels like bio-SNG. Okay? So we tested this. So this is the RDF we have to deal with. As you can see, a lot of carbon and nitrogen, a very good heating value. So there is absolutely value on that waste, which is originally made of residual papers, plastic films, textiles, disposable nappies, and perishable materials. So you can see all those kind of waste plastics, which might have very bad and detrimental impact if landfilled or burned. Here, we try to make an alternative use of those. So this waste feedstock was gasified to produce a syngas, very rich in nitrogen and carbon monoxide. You also have some carbon dioxide, but that's not a problem because that can be separated and thus produce a pure CO2 stream ready to be stored in carbon capture and storage facilities, and that will deliver carbon negative emissions. Okay? The syngas, so namely the carbon monoxide and hydrogen, are catalytically converted into methane and water. Okay, we had a long time operation on catalytic reactors to prove that syngas produced from waste is suitable for bio-SNG production. And with a number of reactors, water gas shift, methanation, I mean, these obviously you will get familiar into this when you will be a chemical engineer. You end up having a final product, which is some CO2 and some pure synthetic natural gas, okay? Which, as you can see here, is very close to the same gas you have in the grid, okay? So that can potentially be used, to make your coffee or to cook your lunch. It's exactly the same grid, the same gas quality, and can be used with the same infrastructure, okay? You don't need to change all the gas heating appliances. In the short, medium term, you can use the same appliances, the same distribution system, just replacing the fossil gas with an alternative gas, which is much more sustainable. Okay. Now, as you've seen, these can be coupled with carbon capture and storage, which will provide that negative emissions. Okay. But you can also decide in the future, I don't want to emit that CO2 anyway. So, because, bio-SNG, methane, even if it's bio, it's burnt anyway. So that produces CO2, even if that was originally biogenic. So it would have a neutral impact on the environment. But you can easily tweak the system and adapt it to produce only biohydrogen and sequester the 100% of the carbon produced, which will give you all those significant negative emissions that are needed to get to the net zero target. So you can see how strong is the impact of this process. Imagine the potential that this could have globally, okay? That's a fantastic opportunity. Obviously, you can transform that syngas produced from gasification into something else. We have a project in collaboration with British Airways where we basically we enhance the hydrogen production by coupling the thermochemical system with an electrochemical system. So with some extra hydrogen produced from wind or solar, so that you would be able to recover and convert the 100% of the carbon available in syngas and produce, for example, methanol or jet fuel, okay? But you can produce gasoline, you can produce LPG, or you can even produce new plastics materials, okay? So that's absolutely critical in delivering the net zero impact in the future. And as you can see, the carbon footprint, considering the entire life cycles of these alternative fuels, is way, way better than the fossil alternatives, but is even much better compared to current biofuels. Because current biofuels like HEFA or ATJ, these are produced from, for example, vegetable oils or energy crops, which have a number of other associated problems with the land use. You know, that land that could be used for food production, or that clean water that can be used for you know, civil use. So that obviously has an impact. And whereas using waste as a feedstock, it has a much lower impact. And indeed, it has a negative impact because you are avoiding those emissions that you would generate if that waste was landfilled. Okay, so that's pretty much it. So to conclude this taster lecture, what's the role of chemical engineering into this? This is part 2. I already partially answered before, but in the very short term, I mean, now, that's absolutely critical. Chemical engineering is that critical sector that will enable the conversion of UK's, and I would say globally largest source of renewable carbon, but also a number of other problematic emissions associated to waste, where not generating those anymore and producing something else, like fuels or materials that could help us as a planet to decarbonize our energy and transportation sectors, and hopefully having a more efficient ways to deal with waste materials. Okay, that's it for today. That's my email address. So if you want to know more about our projects, you can email me, or just be in touch with with the UCL website, where you basically see what the different activities we are involved in to deliver these waste to fuels technologies, and how we help industries to get this. Fantastic. I still see you are quite a few, many people online. So we have sometimes for questions. So we have 20 minutes. So I'll stop sharing the presentations, and I'm open for any Q&As you might, any questions you might have. So I've got one question already, which is, does RDF comprise of only plastics? Absolutely not. Okay. In reality, RDF is mostly biogenic carbon. So it's waste coming from like food waste or paper and cardboard. So all that fractions which end up in being in your non-recyclable fraction of the waste. Okay. Obviously, there is also part which is plastics based. Okay. there is a, depending on country, in the UK is almost 20–30% plastic content. And when I say plastics content, I'm referring to those plastics which are very difficult to be recycled, like plastic films or composite materials or contaminated plastics. Well, these ends up being in the waste and are part of the RDF, which in some sort is kind of good because plastic has a very high energy content, very good energy, very good hydrogen and carbon content, which can be 100% recovered with a thermochemical process, okay? So RDF does contain some plastics, but it contains much more, let's say, biodegradable carbon and hydrogen sources. So second question, how is ash separated from the catalyst in a fluidized bed gasifier? That's a very good question. So ash is a very strong, very large component of waste. It's 20–30% in weight in the amount of RDF. Okay. Now when this enters the fluidized bed gasifier, that's normally it divides into substreams. What as engineers we call it bottom ash and fly ash. Bottom ash is the coarser fraction of the ash which segregates towards the bottom of the reactors and is continuously extracted from the bottom of the reactor. Okay, that's why it's called the bottom ash. That's depending on the type of waste that was treated and depending on the technology itself. That ash can be 100% inert, okay, or it needs some further treatments to be disposed, okay. But you can understand it's much easier to dispose 10 kilograms of ash from 100 kilograms of waste than the full 100 kilograms, okay. That's because the ash is inert, doesn't emit any greenhouse gas, and actually you replenish the nutrients to the soil because it's rich in potassium and calcium and silica, which is good. There is another fraction which is fly ash, which is entrained with the gas, and that's collected in the cyclones and separated. And in the process I showed you that contains plasma, in that case, both bottom ash and fly ash are vitrified in the plasma reactor, okay? So that gives you zero materials to be disposed. Many questions, I'm super happy about that. So what do you think about the future of biomass feedstock to produce fuel in the future globally, not only in the UK? Well, that's absolutely would be critical, okay? Because we obviously having wind turbine or solar panels spread across the globe, that will be fantastic to produce electricity, to produce hydrogen with water electrolysis. But we still need to satisfy a huge demand of fuels globally. Okay, that's because you can easily, well, not easily, but you can potentially convert the road transport into electric cars, okay? This will take time, okay? So you need a solution, an interim solution to be able to have a greener alternative to fossil fuels, bridging the transition towards batteries. But you have another element of sectors for which batteries are not available, and aviation is one of these, but there are also shipping is another fraction. So biofuels will be absolutely important, critical in that. And biofuels, by definitions, are generated from biomass. Now, it's very important that the biomass feedstock is what is called second generation biomass and not first generation biomass. So if you ask me what's the role of biomass, dedicated cultivated biomass just for fuel production, that might be good in the short term, but it needs an alternative because that's not sustainable, okay? Because the land use and biodiversities and water use, that's absolutely critical, okay? you then can, because you can use that land for reforestation or for food or for other stuff. But waste biomass, agricultural waste, forest residues, municipal solid waste, that will be absolutely keys for biofuel production in the UK and globally. Gasification seems like it takes a lot of energy, especially heating materials up to its plasma state. How is it done in a sustainable way? Also, are there waste materials that are produced from gasification, and how can they be disposed sustainably? I will be very quick in my answer because there are so many questions which I want to answer all of them. Well, gasification takes not a lot of energy. It takes some energy, okay? In your questions, you are specifically referring to plasma gasification. But in my presentation, I showed you plasma as a complementary agent, okay? It's what we call plasma-assisted gasification, okay? Plasma is fantastic to get rid of all contaminants, but as you currently pointed out, it's very energy intensive. But if you use that plasma not to gasify your waste, but only to deal with the contaminants like the tars and the ashes, well, that fraction of energy that is needed is minimized to an X%, which can be 5%, which can be 10%, which can be 15% of the energy input, okay? Which is not that bad, trust me. How it is done in a sustainable way, I already answered you. Also, plasma, to power it, you can use electricity, and that electricity in the future can be carbon neutral, okay? So that's a kind of nice integration with that. The vast majority of energy in gasification, however, comes from the addition of a little bit of oxygen, okay? Not enough to burn it completely, but just a little bit to get to the 700 degrees C. Other waste material that are produced from gasification, how can they be disposed sustainably? I already answered in the previous questions. So there is some ash. This can be in the form of bottom ash, which can be inert or does need to be cleaned a little bit before disposal. Or if you have plasma-assisted gasification, you don't have this problem because the ash is vitrified and inertified into a new product, which is not a waste, but it's actually a new product, which is that black rock I showed you. Okay, for the plasma-assisted gasification process, can you explain the major theory behind the plasma converter? As identified that a fluid bed gasifier is used, and traditionally the carbon-to-carbon conversion rate of a fluid bed gasifier is low. However, here the carbon-to coefficient is 96%. What role did the plasma converter play? Very specific question. You guys are almost chemical engineers, which I'm very glad to see that. Very good question. So basically the plasma does provide not only the high temperature, but also the chemically active environment, because plasma is by definition is high temperature, but also ions and electrons, which very good chemical agents against tars. So as you say, the standalone fluidized bed gasifiers, they have rather low carbon conversion efficiency, simply because a lot of that carbon ends up to being either char or tars, okay, which are difficult to be reused. So in most cases are either burned or disposed. Well, that carbon, that chemically active environment does convert that carbon embedded in char and tars, and thus convert them into more carbon monoxide and hydrogen, okay? So that will maximize the carbon conversion efficiencies, okay? And that's why it is very high. What optional modules for the master's program would you recommend to take for the waste to fuel topic? Well, one of these is the module I teach, which is fluid particle systems, which is more widely covered fluidized bed reactors, but there is obviously fluidized bed reactors are widely used in waste to fuel technologies, not just in gasification, but also in pyrolysis or catalytic processes. And that's obviously that is covered in that module. So fluid particle systems is one. There are other models like energy systems, which also covered biofuels, okay? But fluid particle system, the one I teach, is specifically is closely related and relevant to to waste to fuel concept. Have you analyzed residues from RDF gasification? What about their composition? Again, the waste, let's say the waste that you produce from RDF gasification resides mostly in the ash, in the ashes. Now, if it's plasma assisted, as I said, these are not really wasted because you still have heavy metals contaminants, for example, in the ashes, okay? But the good thing of vitrified ash material is that these ceramic residues doesn't have a crystalline structure. It's amorphous. It's like a glass. Okay, glass doesn't have a crystalline. It's amorphous. So heavy metals get entrapped and encapsulated in this vitreous matrix. Okay, and they don't leach out of the solids. So they stays inside. There are obviously some gas contaminants. Okay, think about chlorine, sulfur, which are removed further down into the process in the gas cleaning techniques. Like so, you have obviously liquid scrubbers or dry filter residues, okay, which contains a high fraction of these contaminants. Okay, but they are very, very concentrated. Okay, it's actually so concentrated that can be sent to, for example, a sulfur recovery unit or a chlorine recovery unit. Okay, so you obviously have some waste coming from your waste to fuel processes. Okay, but there are several ways, but the amount are obviously much lower compared to the waste itself. The toxicity is, can be more controlled because it's a more concentrated, and small volumes means that you can more easily cope with those problems. So do you actually burn the solid waste in the gasifier to turn into gas? And what is exactly is heat recovery that is done afterwards? No, you don't burn. It's actually called partial combustion, which is not combustion. I mean, full combustion is your carbon, which react with the oxygen and thus produce CO2. Partial combustion is your carbon, which reacts with some oxygen and produce carbon monoxide, okay? So you obviously produce some CO2 and there is some heat generated by the combustion, okay? But that would say takes up more or less 10–20% of the energy value of the waste. All the remaining is just converted into other flammable gases, okay? Like carbon monoxide, hydrogen, and hydrocarbons. So you just burn a little bit of that. And that's why you produce some CO2, but not as much as you would produce if that would be full combustion. Okay? Heat recovery, obviously heat recovery is important to boost energy efficiency, especially if you have, this high temperature assisted technology like plasma. The gas leaves the reactor, which is normally above 1,000 degrees Celsius, okay? And so you need to reduce that temperature down to a temperature that you can easily couple all the gas cleaning techniques, which comes from 200–300 degrees downwards, okay? And that going from 1100 to 200 degrees Celsius, obviously you can imagine how much of heat you can recover, and potentially, having a small ranking on organic ranking cycles to produce more electricity. Absolutely. Then it's more depend about the scale of the plant and how easily you can integrate all processes among themselves to recover heat. The final synthesis step, also the Fischer-Tropsch. So the process that converts syngas into fuels or into new materials, even that produce heat, okay? And that heat can be recovered either for internal use, okay? To produce steam, for example, because steam is used in many of these unit operation. Or if you produce a lot of that, you can potentially produce electricity. How advanced is the research into microbial fuel cells that are powered from waste? And is it feasible and sustainable for the long term? Okay, that's a good question, although that's not fully my area of expertise, okay? Because I work mostly with thermochemical treatments. Thermochemical treatments, by definition, you need temperature and you need chemistry. So we, in my research groups, we don't work a lot with biological or microbial processes to either convert the waste into fuels or as a fuel cells to produce electricity out of gases. That's doable. That's possible, and we have. There is some work on fuel cells undergoing in our department in the electrochemical innovation labs, more related to biological processes. Also, there is the biochemical engineering department that deals with that. But strictly speaking, in my research group, we deal mostly with thermochemical. I can also tell you why, because thermochemical will be able to be much more flexible in terms of feedstock acceptance, because you can deal at the same time with the waste contaminated plastics. You can deal with the food waste. You can deal with composite materials. You can deal with all at the same time, react more or less in the same way at high temperatures or with catalyst presence. Okay, so that's the reason why thermochemical will play a major role. Okay, because it's much more flexible process, and you can potentially deliver higher volumes of fuels and materials to satisfy the demand. Whoa, okay, fantastic. So if there are not other questions, I thank you very much. I really enjoyed this test lecture, and if you have any other any questions, or you are curious, just curious about what we do, or to know a little bit more on some ongoing projects, drop me an email, and or visit our website, and I'll be more than happy to welcome you. Specifically referring now to offer holders, to welcome you at UCL in the coming years, and thank you very much, and I hope to see you soon in person, and stay well and enjoy the rest of the day. Thank you very much.